Do you hear me? Alright, so it's 8 o'clock, let's start the lecture. We finished with the derivation. So you remember, if we derive the xt, the displacement function, we can get the velocity, and if we derive again the velocity, we can get the acceleration. Let's see an example. Let's derive the 3 times t squared. If xt equal 3 times t squared, you remember the rule of the derivation. If we derive the t over n, we will always get n times t n minus 1. What does it mean? If we derive, for example, the t squared, it's 2 times t, 2 minus 1 equal 1, it's 2 times t. How to derive the three times t squared? The 3 can come out of the derivation, which is 3 times 2 times t, which is 6t. Alright, what does it mean? The velocity, how velocity depends on t, this is 6t. If you create a graph like xt, this 3 times t squared, let's pick up some value like 0, 1, 2. At 0 we are at 0. At 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1. So at 1 we are at 3. At 2 we are at 12. How does the Vt looks like? 1, 2, 2, 3, 4, 5, 6, 7, 8. At 1, at 0, this is 0. At 1, this is 6, 1, 2, 3, 4, 5, 6. And at 12, this is at 2, and this is 12. So, a parabola, if you derive, will be linear t. What about derive it again? So the acceleration is dvt dt. Let's derivate the t. T, we can say t over 1. So this is 1 times t 1 minus 1, which is 0. And that's 1. So if we derive the d6t, the 6 can come out of the derivation, dt over dt, which is 6 times 1, this is 6. So acceleration 1, 2 is a constant. 1, 2, 3, 4, 5, 6. So if we know the xt function, we will know the vt and the at. On the test, I will ask you to derivate and also to show it on a graph how the motion looks like. I hope you are more or less familiar with the derivation. If not, all you have to know is how to derive a polynomial function. Alright, in this math table I can create a picture. Can you write in the Discord whether you see this picture? I can show you where it is. It's here. Do you see the same? Because if you can see it, I can clear the table. Please somebody send me a message in the Discord that you can see it. And if you can see it, you can download it and you have this table as PDF or as image. So it's up to you. Now since I made a photo, I can clear the table and we can continue with the presentation. Here are some rules. But as I've said, you only have to know how to derive a polynomial function. Alright. You can solve it, or we can solve it on the seminar. If you have an xt function, you should be able to answer the question where is the body at given time, or what is the velocity at given time, or what is the acceleration. Let's go back to the math. If we have a function like xt equals 3t squared in the last example, we can find the so-called primitive function. In this case, let's say this is 2t. What is the function? What we derivate, we will get this 2t. The primitive function is the capital Ft, and if you can find out, so if we derive the t squared, we will have 2t. So technically, the capital Ft is the t squared. So based on the math, based on the rules of the derivation, you can find out what is the primitive function. If we know the primitive function, we can integrate. What integration means, or integral? We can have any kind of function. This is t. This is this ft. If we integrate from the t initial to t final, we can have the area under the function. Why is it important? Let's see. We have velocity like 2t. It looks like 1, 2, 1, 2, 2, 3, 4, 5, 6, 7. At 1 it's 2, at 2 it's 4. It looks like a straight line. What if I try to integrate from 1 to 2 this v2 function and used to write here dt because there can be function that depends on different variables, and in this case we want to integrate based on the t variables, based on the time. This is technically the value of the primitive function at the final position minus the value of the primitive function in the initial position. So if vt equal to t, that will be t square final minus t square initial, which is 4 minus 1. What this 3 means? The 3 is the area under this vt. This 3 means the displacement if I start to observe the particle at t1, the t initial to t final. So this is 3 meters. How can we say it in other words? From 1 second, if the vt... Oh, we have some problem with Sarah. Sarah, you said you can't see anything. Can you open at least the YouTube Live? Because in the YouTube Live you should see anything. You can see the smart table on a dedicated browser, but you can also see the smart table in the YouTube Live. Can you send me a message again if you still can't see anything? So back to the delta x, this 3 means observing the body, it moves 3 meters from 1 second to 2 seconds. So this is the delta x. It does not mean we are at 3 meters, so it's not the absolute position of on the xt axis. This is the displacement. How can I determine where is the body right now? I always need to know where the body was at the initial position. So this is the so-called boundary condition. So this is my x-axis. And if I know at t equal 1, at t equal 1 second, I'm here, for example, at 2 meters, I can calculate at t final, which is 2 seconds, this is 1 second, I'm at 5 meters, because the delta x is the integral. So at integral, I always check the boundary condition. The others, do you see the live and the smart table? Just write something in the Discord. So I take a picture again and I will clear the table. Alright, unfortunately I double-clicked on this final slide, but you don't have to, of course, download both. How can we solve? So we can solve the equations of the kinematics if we know the xt. From xt we can have vt, from vt we can have acceleration. So this is the easiest way, from xt to vt to at. This is easy. If we want to go backwards, so this is means we derivate at every step. From at to have the vt and from vt the xt, we have to integrate. Integrating is not that easy, but we can survive. Why is it important? Because in the real life situation, we mainly know the acceleration. Why? Because we have forces, and you know, or in this lesson we will learn about it, if you divide the force with the mass, you can have the acceleration. If we have the acceleration, we can go through this chain by integrating 2 times, and at the end you can have the path of the particle. Alright. The integral is something useful in the kinematics, but there are many other kind of integrals. So what we use here is the line integral, but there can be double, triple integral. We can integrate a surface or a volume also. Alright, let's solve an example and check it. Why should we be careful with the boundary conditions? Alright, so what we know, acceleration is -10. We are only in one dimension, so means if we have an x-axis, wait, if we have x-axis, the acceleration goes opposite to the positive direction of the x-axis. But of course, the unit of the acceleration is meter per square and not meter. So, how can we find out where is my body? What should I need for that? I have to add the initial conditions. For example, at xt initial, we are at 50 meter, and my initial speed is 20. That means I'm somewhere here at 50 meter. This is my acceleration, but my velocity is also positive, so I move to the positive direction of the x-axis, but the acceleration is on the opposite side, means I will slow down. So this is my v equal 20 meter per second. Wow, close to the edge of the smart table, it can't really recognize my writing. Alright, what should I calculate at first? Since I have the acceleration in one step, I can only calculate the speed, technically, the changes of the velocity. T1, and let me write T final or T at the end. Oh, let's write T final. So, let's integrate the -10 from T initial to T final. A constant, if the function is a constant, its primitive function is a linear term. Let's say -10t, and with this sign initial final, it means I have to have the -10t final and subtract the -10t initial. I can also add that, for example, the initial is at 0. How does it look like? So because of the t initially 0, I can forget this second part, and this is minus 10 t final. We can say the t final is, for example, 2 seconds, or we can keep it as parameter. What we know again, the changes of the velocity is minus 10 t final. What does it mean? For example, if I start... Alright, thanks Sarah to let us know that you are okay now. Alright, so what does it mean? If my t initial is 20 meter per second and the initial is 0, that means at t equals 0 my speed is 20. At t equals 1 it will be less. Oh, let's write it. So how the speed depends on time means, just a minute. The speed is the delta Vx plus my initial speed. This delta Vx is minus 10 Tf plus 20. So for example, at t equal 2, my speed is minus 20 plus 20 equals 0. Means at t equal 2, I'm stopped. But for example, at t equals 3, my speed is minus 30 plus 20 means minus 10. So I start to move backwards along the x-axis. So if I know the delta x and the initial, I can have the correct function of the v. Let's say at the very beginning I don't want to say whether I want to check the speed at t equals 0 or t equals 2. Let's just say I want to know the speed at any t. So let's replace the t final with t. If I have the vt, so this is the final form of the vt, integrating from t initial to any t, you can write here t final or only t, gives you the delta x. What if I integrate this 20 minus 10t, integrating the 20, so let's see the primitive function, it's 20t minus 5t squared. If you believe me that this is the primitive function of 10t, but if you can't, let's derivate the 5t squared. You know the 5 can come out, then times 2t, which is 10t. And I have to have this primitive function at tf, or we can say only t. So this is 20t minus 5t squared minus 20t initial minus 5t initial. You can write here final if you want, but at the very end we will replace it with time. We are lucky because t initial is 0, so this part will be 0. So the final form of the dx is 20t minus 5t squared. We still don't know what is the correct form of the xt. I take a picture and clear the upper part of the table. For example, this one. So the correct form is the xt is the initial plus delta x. Initial is 50, delta x is 20t minus 5t squared. So the xt will be 20 plus 50 plus 20t minus 5t squared. So, what question we ask? If we have a constant acceleration and the initial position is 50 meters and the initial speed is 20, the particle will move like 50 plus 20t minus 5t squared. So if we ask, where is the particle, for example, at 1 second, it's 50 plus 20 minus 5, which is 65. Where is the particle at 5 seconds? It's 50 plus 100 minus 25, 125. This is 25. And since we use SI everywhere, this is meter. So, if we know the acceleration and if we know these boundary conditions, we can have the position of the particle, which is an answer for this example. Photo again, and I clear the table. So in the test, you will find at least these two examples. I will give you the xt, please give me the at, which is easy, you have to only derivate 2 times. But if I ask, I know the acceleration and the initial speed and the position, please tell me what is the function of the x. You will be able also to do that. Let's go further with the presentation. Yes, integral is something we use every day. So for example, if you check how your phone identifies faces, that also needs a special integral, not analytical integral, what we use here, but so-called numerical integral. There is a nice YouTube video how the convolutional neural network works. It uses integral several times to find the faces in a photo, and since you can use your phone and you can identify faces, it works. Alright, exercise. These exercises are for homework. So if you are familiar with the supercars, you can see I have a Taycan. From 0 to 200 km per hour. It takes 9.8 seconds. Let's say the initial position is 0, the initial speed is 0. Where is the Taycan when it reaches this 200 km per hour? You know the acceleration, you can have the function of the Vt, and then you can have the function of the position, and you can answer these questions. So please start a doc and try to do this example at home and send it to me, let's see, even on the Discord. Alright, I mentioned that many cases we know the force. You know there are a lot of forces like gravitational force, spring force, Coulomb forces, Lorentz forces, and so on. If we derive with the mass, we can have the acceleration, and from the acceleration we can have the velocity, and then we can have the position. Well, what is this m? There are two words for this M. One is mass and the other is weight. These are technically two different quantities, but since Einstein's general relativity, it can be proven that these are technically the same things. So, what is the weight? If you stand up, the force you push the floor, let's say you are 70 kilogram, you multiply it with the small g, the acceleration of the gravitational field on the surface of the Earth. So let's say this is 10, and m times g is 70. The unit of the weight is force. So if somebody asks you what is your weight, you should multiply your mass with this g and answer it's 700 Newton. The mass is something different. The mass, by definition, is what we write here. The mass is so-called the resistance to be accelerated by a force. What does it mean? If I have 100 Newton and a body with 10 kilogram, it will accelerate like 10 meter per square. So let's say this is a small weight. It means a small resistance against the force. Small resistance means large acceleration. If I have a body with 100 kilogram, acceleration will be smaller. So it means more resistance against the force. So weight is something you push the floor, and its unit is Newton, and this inertial mass is the resistance against the force. The larger inertial mass means smaller acceleration using the same force. We have to mention, it's not too much to know, but we have to mention there are two kinds of collisions, elastic and inelastic. We use this elastic collision like in billiard. In billiard, there are two kinds of conservation, the energy conservation and momentum conservation. And we can use this elastic collision to describe several phenomena in the physics, like ideal gases. So what does it mean? If I have a body here, a moving body A with small mass and a larger body B, if I want to calculate its momentum, and we will go back to what is momentum technically right now, this is m times v. The system, which is the two body A and B, before and after the collision, the system shouldn't change the quantity of the sum of the momentum. And it works when I move the small ball towards the large one, or upside down, I have a moving large ball, like bowling ball, and hits the ping pong ball. Alright, so the momentum is m times v. M times v. If I have a system like body A and body B, let's suppose both moving, mass B, mass A, the sum of the momentum is mass B times V, B plus mass A times VA. And if there is no external forces, this is the only system we observe, and it's separated from the environment. This sum of the momentum shouldn't be changed by any collision. Perhaps you've seen these swinging balls. This is a popular demonstration. After the lecture, you can click on this video. I found a super movie where you can see how a swinging ball moves. And what I mentioned, the momentum is m times v. The kinetic energy, perhaps you know, this is 1/2 mv square. And in this system, since this is elastic collisions, also the momentum and the kinetic energy should be the same before and after the collision, and this is the reason why it moves like this. So for example, even we can conserve the momentum by a incoming ball with v and the outgoing two balls with v/2, but in this case you do not conserve the kinetic energy. Alright, so what we have: observations, what is momentum, what is force, what is mass. And Newton was the physicist, they summarized it. Let's say there is a so-called inertial frame of reference, which means if there is no forces act on the body, its body keeps its velocity constant. You remember its velocity? So this is a vector. Oh sure, I checked the Discord here. Of course, you can, at the end of the lecture or even right now, you can download the screenshots of my presentation from your browser. But I will also save it and put it somewhere to be sure we saved everything for the future. So what is Newton's law again? Sorry, I was interrupted by myself. If there is no external forces, alright, I was misunderstood something, not the screenshot, other notes with the exercises. Oh yes, with the next Neptune message. Oh, just a minute, I can do it right now. This presentation is in my Dropbox folder. One second. I open the Neptune and you will see this presentation also. So in a minute I will send you the PDF of the lecture 3. Please check your Neptune message and let me know if you can't download, but I'm pretty sure you will be able. Alright, go back to Newton laws. Alright, so the first is the law of inertia, means if there are no external forces, the body won't change its velocity. Since the body, in this case, won't change its mass, it means the momentum is conserved. The next one, if there is an acceleration, so technically this is the third one, if there is an acceleration, we have to divide the acceleration with the mass, inertial mass, and then you will have the, if there are external forces, you have to divide the force with the mass, and you will get the acceleration. From the acceleration, you can calculate how the velocity, or in this case the momentum, will be changed. So this F equal m times a connects the forces with the acceleration, and how we started this lesson. From the acceleration you can calculate how the particle will move. When there is, for example, a collision, and one body exerts a force on the second body, the second body also exerts a force to the first one, and the magnitudes are the same, but the direction is opposite. So let me check the moment of the collision. Two particle moves A, B, with mass B, mass A, and here, if there is a forces F, B exerts on A, there is also forces, that's right here. So this is the forces that B exerts on R, and this is the forces A exerts on B, and technically they have to be the same magnitude. They can change only if we talk about, yes, it's right, but the direction is opposite. I think you all knew it before. The first force flow means if there are no more forces like F1, F2. This is why we learned about vectors last time. The sum of the forces can be calculated by only adding the two vectors. And of course, if there are even more forces, the sum of the forces is the vectorial sum of all forces, and we can go with these forces to the Newton's third law. If this is a force, divided by m, we can have the acceleration and we can have the velocity. These are the so-called real forces, but for example, we can travel several times when your coordinate system, the internal part of the car or the bus or the tram, it is accelerated. There are so-called non-inertial forces. Non-inertial forces means these are not real forces, but also can cause acceleration. In this case, we can't talk about inertial system, so the Newton laws are not valid in the non-inertial frames. This is why we started with the definition of inertial frame of reference here, because Newton laws only valid in inertial frames. So please don't try to use Newton laws for example, as here in the example for accelerating trains, because in this case, for example, the second law, which is this one, is not valid because there is no other forces. You can observe a particle which feels the forces, but there is no other forces. The simplest non-inertial force is the accelerating train or accelerating cars, but there are also forces we can feel less, but if we observe a flying particle on the surface of the Earth, you can see the centrifugal forces or Coriolis forces. The most attractive example for Coriolis forces is the Foucault pendulum. Perhaps you learned about it. If not, please Google it. More than 150 years ago, it was shown that the Coriolis forces is something you can see, even you can't feel it by the daily motions. There was a very long pendulum in Paris, and it changed the plane of the motion in Paris, let's say with 264 degrees in a day. There are lots of nice video how Foucault pendulum moves. It depends on we haven't learned about it, but we'll learn. This omega, this is the angular velocity, and since the angular velocity is a vector, which is the maximum at the north, and at the equator, it's perpendicular to the motion of the plane of the pendulum. We have a full circle in 24 hours at the north with this Foucault pendulum, and it won't move at all at the equator. What about forces? We can talk about, of course, gravitational forces like frictions, forces in the fluids. We try to stop the motion of the fluid. But technically, if we go deep inside, there are only a few forces. One is the gravitation, and the rest, the weak, electromagnetic, and strong, these forces can be put in the same framework, which we call standard model. So right now, we think that at the beginning of the universe, like at the Big Bang, there are only perhaps two forces. We don't know anything about the gravitational forces. I mean, of course, we know how it works, but by theory, we can't understood absolutely what gravitational means. But these weak forces, which is the, for example, beta decay of the atoms, electromagnetic like Coulomb and Lorentz, and strong forces, this is the forces inside the nucleon. It's very strong forces, but its length is very small. So these forces seems to come from one forces, but at very high temperature, for example at the temperature of the Big Bang. So it's a very interesting part of the physics. Right now we think there is only one forces plus the gravitation, but this is only true at very high temperature, and now at room temperature these forces somehow were separated into more forces, but we can observe like weak forces, beta decay, electromagnetic, the Coulomb forces, and the strong forces. So these are the forces we can feel: the spring, Coulomb, Lorentz, gravitational, of course the friction. We will learn a bit more about friction in the next lessons. And we will continue with the motion in 3D next time. Did I save the last one? Yes, I think I did. So, any questions? So, I think I can hear you, so let me know if you have any question with these things. If not, I can wait a bit, but just talk a bit. On the seminar, I know, so this is YouTube Live, Discord. Perhaps you are too shy to send me a message on the Discord, but we can go into the details and I can answer the questions during the seminar Wednesday and Thursday. So till that, you should practice the integral, because we will integrate things like these ones. And just think 5 seconds about mass and weights, that these are two different things. And of course, just take a look at the Newton's law, because this is the axioms of the motion, and the modern physics based on this kind of axioms or laws. We use it several times. The rest is just for your interest. Alright, once again, any question, or we can stop this lecture now? Alright, if there are no questions, I stop now.